In the winter of 2019, one of the most famous stars in the night sky began to disappear. Not quickly, not dramatically, slowly, over weeks, the star that marks the right shoulder of Orion, visible to the naked eye for all of recorded human history, mentioned in texts from ancient Mesopotamia, used as a navigation point for sailors for millennia, began to dim. By January 2020, it had lost approximately 2/3 of its normal brightness. A star that should have been one of the 10 brightest in the sky had faded to the point where it barely ranked in the top 20. Astronomers called it the Great Dimming, and for several months, the entire global astronomical community held its breath, because Betelgeuse is not supposed to be here. Not in the sense that it is unwelcome, in the sense that, by the most straightforward reading of stellar physics, by the logic of what happens to a star of its mass and age and composition, Betelgeuse should have already exploded, should have already become a supernova, the most violent stellar explosion in the observable universe, scattering its outer layers across hundreds of light years, briefly outshining the entire Milky Way, leaving behind a dense spinning neutron star where a red supergiant once burned. Astronomers have been predicting this for decades. The star has not cooperated, and the Great Dimming, the most dramatic change in Betelgeuse's behavior in the era of modern observation, raised a question that the entire field of stellar astrophysics was not fully prepared to answer. Was this it? Betelgeuse is not a normal star. It is a red supergiant, one of the largest stars known to exist, a category of object so extreme that the numbers describing it strain ordinary comprehension. Its radius is approximately 700 times that of our Sun. If placed at the center of our solar system, its surface would extend past the orbit of Jupiter. It would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and most of the way to the gas giants. It is approximately 700 light-years from Earth, close enough to be studied in extraordinary detail, far enough to be safe. At that distance, a supernova would be spectacular, easily visible in daylight, bright enough to cast shadows at night, visible for months, but not dangerous. The radiation and particle flux from a supernova at 700 light-years, while detectable and scientifically interesting, would not significantly damage Earth's atmosphere or pose any direct biological threat. Betelgeuse is approximately 8 to 8.5 million years old. This sounds ancient. By the standards of stars like our Sun, which will live for 10 billion years, it is not. Red supergiants burn their fuel so rapidly, fusing elements in the sequence that leads toward iron, that their entire lifespan is measured in millions of years rather than billions. And Betelgeuse, by the best current estimates, is near the end. How near is where the uncertainty lives. The life of a massive star is a sequence of nuclear burning stages, each shorter than the last. After hydrogen fusion exhausts the core's hydrogen supply, the core contracts, heats, and begins fusing helium into carbon. After helium is exhausted, carbon fusion begins, then neon, then oxygen, then silicon. Each stage releases less energy per reaction than the one before. Each stage lasts a shorter time. Hydrogen burning in a star like Betelgeuse, approximately 8 million years. Helium burning, a few 100,000 years. Carbon burning, perhaps 1,000 years. Neon burning, a year. Oxygen burning, months. Silicon burning, days. The final stage, silicon burning to iron, lasts approximately a day. Then the iron core collapses in less than a second, and the supernova begins. The progression from carbon burning to collapse is so rapid on astronomical timescales that by the time a star is visibly showing signs of late-stage nuclear evolution, the end is already cosmically imminent. A star burning carbon is within a few thousand years of death, a star burning neon within a year or two. Betelgeuse is showing signs of being in the late stages of this sequence. Its behavior, the variability, the dimming, the complex pulsation patterns, is consistent with a star in the later phases of nuclear burning. Exactly which phase is difficult to determine from the outside. We cannot look into the core. We measure the surface and infer the interior. The best current estimates place Betelgeuse's supernova somewhere between 100,000 years in the future and at the earliest end of the uncertainty range, potentially as soon as a few thousand years. Not tonight, probably not this century, possibly not this millennium, but in the timescale of a civilization, soon. The great dimming of 2019 and 2020 was not the first time Betelgeuse had behaved strangely. The star is a variable. Its brightness oscillates on multiple timescales, driven by complex pulsation modes, convection in its enormous outer envelope, and the ejection of material from its surface. It has been known to vary for as long as systematic observations have been made, but the magnitude of the 2019 to 2020 dimming was unprecedented in the modern observational record. At its minimum, Betelgeuse had dimmed by about 2.5 magnitudes, an enormous change for a star that astronomers have been watching carefully for generations. The question of what caused it occupied dozens of research teams simultaneously, generating papers at a rate that reflected the global significance of the event.
Two explanations emerged as the leading candidates. The first was a surface cooling event, a giant convective cell on the star's surface, analogous to a sunspot but on a scale that dwarfs anything in our own solar system, temporarily reducing the local surface temperature and suppressing the brightness. Betelgeuse is known to have enormous convective structures. The star's convection operates on scales where individual cells can be as large as the entire sun. The second was dust, material ejected from the star's surface, cooling as it expanded outward, condensing into dust particles that blocked the star's light from our line of sight. A localized dust cloud, moving across the stellar disk as seen from Earth, temporarily obscuring a significant fraction of the visible surface. Subsequent analysis, including observations from the Hubble Space Telescope, supported a combination of both: a surface mass ejection, a large eruption that threw material off the stellar surface, cooled to form dust as it expanded away from the star, while the surface beneath the ejection site also cooled significantly as a result of the disruption. A surface mass ejection, not a gentle event, an eruption that threw hundreds of thousands of the mass of our moon into space in a relatively short period. Not a supernova, but not nothing. The Great Dimming ended. By April 2020, Betelgeuse had returned to approximately normal brightness. By late 2020, it was brighter than average, and then in 2023, it became brighter still. Betelgeuse reached brightness levels not seen in the modern observational record, exceeding its historical maximum, outshining stars it had not outshone in living memory. Astronomers monitoring it watched the brightness climb with a combination of scientific excitement and the specific unease of watching a patient whose vital signs are behaving unexpectedly. Bright is not necessarily good. Bright can mean the star is in a phase of enhanced activity. Bright can mean the surface is behaving differently from its normal pulsation cycle. Bright can mean something is happening in the interior that is manifesting as increased luminosity at the surface. Or bright can simply be a phase of the star's normal multi-year variability cycle, temporarily aligned to produce higher than average output, signifying nothing in particular about the stellar interior. We cannot tell from the outside. This is the central frustration of studying Betelgeuse. The star is one of the most intensely observed objects in the sky. It has been monitored continuously for generations. Its light curve contains more data points than almost any other variable star. Every anomaly is noted, analyzed, published. And yet the interior, the core where the nuclear burning is occurring, where the progression toward iron and collapse is happening, is completely inaccessible to direct observation. We see the surface, we infer the inside. There is a way to see inside a star, not with light, with neutrinos. Nuclear reactions in stellar cores produce neutrinos, ghostly particles that interact so weakly with matter that they pass through the entire stellar interior and escape into space in seconds, carrying information about the core conditions at the moment of their production. A star producing neutrinos at the rate that late-stage nuclear burning generates them is, in principle, detectable by neutrino observatories on Earth. The problem is sensitivity. Betelgeuse is 700 light-years away. The neutrino flux reaching Earth from its normal nuclear burning is too low to detect above background with current instruments. We can detect neutrinos from supernovae. When SN 1987A exploded in the Large Magellanic Cloud in 1987, approximately 168,000 light-years away, neutrino detectors on Earth registered a pulse of approximately 24 neutrinos in the span of a few seconds. A tiny number, but a real detection. Betelgeuse at 700 light-years is much closer than SN 1987A. A supernova in Betelgeuse would produce a neutrino signal detectable by current observatories minutes to hours before the optical brightening, before light could escape through the stellar envelope. The neutrinos would arrive first because they escape the collapsing core in seconds, while the shock wave takes hours to reach the surface. We would know it was exploding before we saw the explosion. But the normal nuclear burning of a living Betelgeuse, even in its late stages, is below current detection thresholds. If silicon burning begins in Betelgeuse's core, current models suggest the neutrino flux might increase enough to be detectable by the most sensitive instruments, maybe under favorable conditions. We are not certain we would see the warning. In 2023, a paper was published that attracted significant attention in the stellar astrophysics community. The authors, analyzing a combination of photometric, spectroscopic, and astrometric data on Betelgeuse, proposed that the 2019 to 2020 great dimming and the subsequent unusual brightness behavior were consistent with the star being in a more advanced stage of nuclear evolution than previously thought. Specifically, they argued the data was consistent with Betelgeuse currently burning carbon in its core, a stage that, if correct, would place the supernova not in tens of thousands of years, but within a time frame measured in centuries.
The paper was contested. Other researchers disagreed with the interpretation of the data. The stellar models have uncertainties large enough that distinguishing between helium burning and carbon burning phases from surface observations alone is genuinely difficult. The community did not reach consensus, but the paper was published in a peer-reviewed journal. Its authors were credible researchers. Its methodology was scrutinized and not definitively refuted. The possibility that Betelgeuse is closer to its end than the standard picture suggests, that the Great Dimming was not a surface event in a comfortably far from death star, but a symptom of a star in more advanced decline, was not ruled out. We do not know which interpretation is correct. What does a supernova in Betelgeuse look like from Earth? Brighter than the full moon. Some estimates say significantly brighter, potentially visible in daylight for weeks, visible at night for months before fading below naked eye visibility. A new light in the sky, fixed in position unlike a planet, steady unlike a meteor, growing brighter over the first days and then slowly fading over weeks and months. Orion would look different. The right shoulder, one of the defining features of the most recognizable constellation in the northern sky, would be replaced by a point of extraordinary brightness, then nothing visible to the naked eye. Then, over years, a slowly expanding nebula detectable by telescope. The supernova remnant would be visible for thousands of years. The Crab Nebula, the remnant of a supernova observed in 1054 AD, recorded by Chinese and Arab astronomers as a new star visible in daylight for 23 days, is still visible today, nearly 1,000 years later, as an expanding cloud of gas and synchrotron radiation spanning light years. Betelgeuse's remnant would be larger, brighter, closer, a feature of the night sky for millennia. And at the center, almost certainly, a neutron star, possibly a pulsar, rotating rapidly emitting beams of radiation that sweep across the sky every fraction of a second. A city-sized remnant of something that was hundreds of times the size of our sun, spinning in the middle of its own debris cloud. Betelgeuse has been in the night sky for every human civilization that has ever looked up. The ancient Egyptians saw it. The Babylonians named it. Medieval Arab astronomers called it Ibit al-Jawza, the armpit of the central one. When European astronomers transliterated the Arabic star catalogs, the name corrupted through several steps into Betelgeuse. It has been in every star atlas, every astronomical textbook, every guide to the night sky since the field of astronomy existed. And for all of that time, for every moment of human history in which any person has looked at Orion, Betelgeuse has been running down. The silicon that will become iron when the core finally collapses has been accumulating in the star's interior since before our species existed. The nuclear clock that will eventually trigger the most violent event visible from Earth in recorded history has been running since the star formed approximately 8 million years ago. Every night that Betelgeuse has been visible in the human sky, it has been closer to its end. We just do not know how close. There is one more detail that sits uncomfortably in this picture. The light we see from Betelgeuse tonight left the star approximately 700 years ago. We are not seeing Betelgeuse as it is. We are seeing it as it was in the early 13th century, around the time of the Black Death, around the time of Dante and the earliest European universities. Whatever Betelgeuse is doing right now, at this moment in real time, we will not know for 700 years. If Betelgeuse is already in the process of silicon burning, if the core is already hours or days from collapse, we will not see the supernova until the light reaches us. We will not have any warning. We will simply see Orion one night and then see it differently the next. There is a non-zero probability, small, not well constrained but real, that Betelgeuse has already exploded, that the core has already collapsed, that the shockwave has already begun its journey outward through the stellar envelope, that the neutrino burst has already passed through our solar system undetected, that the light front is already on its way, crossing the last of those 700 light years, and will arrive at Earth on a night that has not yet come. We are not watching Betelgeuse in real time. We are reading a letter written 700 years ago. Go outside on a clear winter night and find Orion. The three belt stars, Alnitak, Alnilam, Mintaka, in a nearly perfect diagonal line. Below them, the faint smudge of the Orion Nebula, a stellar nursery where new stars are being born right now. Above the belt, the two bright stars marking the shoulders, Bellatrix on the left, Betelgeuse on the right. Betelgeuse is orange-red, distinctly so, noticeably different in color from the blue-white stars around it. The color of a star near the end of its life, its outer layers expanded and cooled to temperatures that shift its light towards the red. It does not look like it's about to explode. It has never looked like it's about to explode. It will not look different on the night before it explodes than it looks tonight. The warning will not come from looking. It will come from neutrino detectors, if the detectors are sensitive enough. It will come in the form of a pulse of nearly massless particles passing through Earth at the speed of light, registering in underground tanks of water and ice, interpreted by physicists who will immediately understand what they are seeing. A supernova alert, sent to astronomers worldwide, minutes to hours before the light arrives. That alert system exists. It's called S-News, the Supernova Early Warning System. It has been operational since 2005. It connects neutrino detectors on multiple continents into a network that would recognize the simultaneous signal of a galactic supernova and alert the astronomical community immediately. It has never been triggered by a real supernova. It is waiting, the way everything in astronomy waits, patiently, watching, storing data, ready for the signal that may come tonight or may come for 100,000 years. Betelgeuse is up there, still burning, still dimming and brightening in its complex variable pattern, still keeping its interior secrets from every instrument we have pointed at it, still running down. The letter is 700 years old. We are still reading it, and somewhere in the space between what it says and what is actually happening right now, the star is doing something we cannot see, something that will eventually reach us on a night that has no name yet.